I will start with, this will be 5 times 10 to the 2, that's 45, as I know, right? And then this will be 100. 100, no, 200.5. And then for 2 blue, that will be 5, choose 2 times 10, choose 1. Again, because you will need to select 3 markers and 2 of them blue, then the other one has to be not blue. Five choose 2 is 10. That's 100 over 455. And then last one, 5 choose 1 times, I'm sorry, 5 choose 3 times 10 choose 0 over 15 choose 3. That will be 5 times 1 over 455. That's 5 over 455. Now, at this point, use your calculator. Try to make sure that the total is 1. So at least when you add these fractions, 120 plus 225 plus 100 plus 5, can you confirm that this is 455? I think I made a miscomputation somewhere. Because this does not give me, this does not give 455. This again, my bad. This should be 10. What am I doing? 5 choose 3 is 10. Good thing I checked, right? Now, when you add this, you get 455. Okay? So we know that they will add up to 1. Now, then we will reduce. I will reduce this. I know they add up to 1 already, so I'm actually ready with my frequency. I'm sorry, probability distribution. Okay, so x, this is 0, 1, 2, 3. This is the probability. Okay, now you can use 120 over 455 and on. Okay, but for the purpose of our extension, I suggest you to reduce it, but do not fully reduce that. Do not fully reduce it. Reduce it such that they all have common denominator. Reduce that such that they have all common denominator. So take a look what kind of common factor they have on these numbers. Can anybody help me? What is the common factor of these 8 numbers? Actually, only 5. Only 5 numbers. The least common the common factor is 5, which means I can reduce by 5. If I reduce by 5, this will be 24 over 91. Reduced by 5, this is 45 over 91. 20 over 91. And then 2 over 91. Now that's the one, that's the numbers you put here. Can I not reduce any commas? Yeah, that's fine. I just think it's not a good idea for you to make it into decimal. And you will see very soon why I don't recommend you to make it into decimal. When I add this, I get 91 over 91. So I confirm that's a frequency distribution. I mean, probability distribution. Now, then I will extend this to find the mean and the variance. Okay, so the first extension will be px. This is 0. Now, when you multiply these fractions, they already have common denominator, and we will keep the common denominator. When you multiply this guy here with the top. this guy with the top, this guy with the top. Suddenly I need to teach you a little bit arithmetic. Okay, why? Because, for example, 2 times 20 over 91, that's the same to say 2 over 1 times 20 over 91. Now, since I want to keep the denominator anyway, so I will not try to cancel it even if I can. Therefore, I will just multiply the top with the top. Okay? Then this will be 45 over 91, 40 over 91, and then 6 over 91, which when I add up, they happen to be 91 over 91 also. They happen to be 91 over 91 also. Okay? Usually not. Usually not. Usually not. That's just coincidence. Of course, the total probability has to be 1. This guy here has to be 1. Otherwise, either something wrong, something some miscomputation, like what I did earlier. Good thing I checked. Okay. Or I missed some effect, maybe, just in case. Okay. But the total of px doesn't have to be 1. In this case, it just happened to be 1. So the mean here will be 91 over 91, which is 1. Now, how about the standard deviation? To get the standard deviation, I need to extend this using the second extension. Okay, that is x squared and px squared. 0 is 0. This would be 45. I'm sorry, no, that's not. That's 1. 1 squared equals to 1. 2 squared is 4. 3 squared is 9. Now then I will multiply the probability and the x squared to get this part. Probability and the x squared to get this part. We did this before, right? Last week and the second week of class, when it were frequency distribution. So this will be 45 over 91. This is 80 over 91 and 18 over 1. Okay. Notice that I just multiply with the numerator such that the denominator stay the same. Okay, and now when I add them, I get 143 over 91. I will just leave it like that for now. Okay, the variance is 143 over 91 minus 1 squared. Okay, the variance, the formula for variance is the sum of px squared minus the square of the sum of px. Okay, I hope you remember that. Then from there, if you want to use calculator, go ahead. So basically, this would be plus 9, so it's 52 of 91, such that the standard deviation will be the square root of that. If you want to make it decimal already earlier, that 52 over 91, if you want to convert that to decimal, go ahead, and then you do the square root. Okay, 52 over 91 give me this decimal, 0.57143, and then the square root of that gives me 0.75593. That's the standard deviation. This is the mean. Happens to be a very nice number for the mean. That's for number 4. I go on to number 5. Number 5, the probability of B, probability of A given B, probability of B given A are given. So let's see how to get probability of the intersection. Now this question number 5 here is actually considered hard. Well, of course it's easy for me. Okay, and if with some training, it becomes supposed to be very easy for you. But those who don't study, they can't even do part A. The problem with this, the issue with this problem is your part B depends on part A. Your part C depends on part B. Okay, your part B in this case depends on part A, and your part E depends on part D. Okay, in other words, if you can't do part A, forget the rest of the question. So you basically, if you cannot do even part A, forget these 13 points. Forget these 13 points. Okay. Now, of course, then I don't like this question because if you miss any part of that, then you basically miss the rest of that question. But at the same time, it also means this question is crucial. Okay, I scaffold that for you. In my final, I may, instead of asking A and B and D, for example, I just jump right away asking you part E. Now, at that time, then you need to know what to do first, what to do next. Now, to answer this question, I need to find probability of A intersection B. Let's find out first from the formula. Probability of A given B is equals to probability of D intersection over probability of B. Now, probability of B given A is probability of D intersection over probability of A. Now, the thing is, the one in question is probability of the intersection. That's the one in question. And the one given, probability of A given B, probability of B, probability B given A. Those are the one given. So you see, we won't be able to do part A using this formula. It won't work. Why? We don't know this thing. And of course, we don't know the intersection. If you have two unknowns in your equation, then we won't be able to do that, right? Okay, it's clearly that we know A given B and probability of B, which enable us to find the probability of the intersection. So that's the formula I will use. Okay, probability of A given B equals to probability of D intersection over probability of B. Now then I plug in numbers. This is 0.3 equals to probability of intersection over probability of B, which is 0.5. So 0.3, I multiply by both sides by 0.5. That's probability of D intersection, which is 0.5. Now, the thing is, once we get the probability of the intersection, all of a sudden, this part is known. All of a sudden, this part is known, and we can use this formula here to find part B. Okay, probability of A. So probability of B given A equals to probability of D intersection over probability of A. Now I plug in numbers. This is 0.4 equals to probability of D intersection over probability, oh, I'm sorry, I plug in numbers. So this is probability of 0.15 over probability of A. 0.4 times probability of A equals to 0.15. Therefore, probability of A is 0.15 over 0.4, which, using your calculator, I believe that's 0.375. Now, once you have probability of A, probability of B, probability of intersection, then we can answer probability of the union, which is probability of A plus probability of B minus probability of the intersection. Okay, that is 0.375 from part B plus probability of B 0.5, that's given, minus probability of the intersection 0.15 from part A. That would be 0.725. Now, how about probability of not A but B? To answer that, let's first take a look on the Venn diagram to help us discover the formula. If this is A and this is B, then not A but B refers to this region here. This is not A but B. We don't know yet what's that, but we can compute it in the following way. What I will do is I get the whole B's. I will get the whole B. What is probability of B? 0.5, right? And then you cut this away. You cut the intersection away. Then you will get probability of B outside of A. Now, but the Venn diagram is not acceptable work though. It just helps us to recall or rebuild the formula, which is probability of B minus probability of the intersection. That will be 0.5 minus 0.15. Okay. Now, finally, what is the probability of B given not A? That's probability of the intersection not A but B over probability of not A. That is equal to 0.35, that's from part B, over 1 minus probability of A, which is 0.375. Maybe I write it here first. This is probability of not A intersect B over 1 minus probability of A. Okay, using calculator, we get 0.56. Now that's for this number 5. I usually have question number 5 in my test. In fact, all the problems that I go over here are very common problems. You will see my test 2, even though that's still considered one of the hardest tests. In my opinion, test 2 is the hardest, but some students say test 3 is the hardest. But all of us agree that test 2 and test 3, even if they are, one of them is more difficult than the other, both of them are actually closely, like they are how to say, the difficulty level almost the same. Okay, the difficulty level for my test 2 and my test 3 almost the same. Now, I think recently I tried to streamline my test 2 such that you see more common problems. Okay, so let's say you will have 8 problems from in my test 2, then one of them something you've never seen maybe, or you've seen before but not consistently showing up in all my test 2. But of all of 8 problems, you will see that at least 5 of them always show up. Okay, and I can tell you the one always show up. The one always show up is number 3 shows up in the last 4 years, I think, or even 5 years, in the last 4 years, shows up consistently. Number 4 always show up, but I do change, like for example, sometimes I make it with replacement becomes without replacement. Without replacement suddenly becomes with replacement. I play with that. Okay. And question number 5, as I know that has been the type of question I always ask in my test 2. In the last 6 years, I asked question number 6. Okay, and later on, you will see question number 2 is a question I asked, I think in the last 10 years. In the last 10 years, I almost always ask that question. Okay, so the problems I go over in this fall 15 test 2 are actually questions that if you see my other test 2, you will see most of them again, of course with different numbers, okay, with slightly different scenario. Okay, and you will see if you take a look on fall 15 this test 2 again, you will see my test 1, I mean my question 1 is something I always ask. Okay, let's do number 6. A game of lucky triplet draws 3 markers without replacement. So again, we have 3 markers without replacement. From a box containing 12 identical markers, we have 5 black, 4 blue, 3 red. 5 black, 4 blue, 3 red. So it's markers again, huh? I think in the past I changed that markers into soda, lucky soda. So instead of 5 blacks, 4 blue, 3 reds, I think I once make 5 Coke, and then 4 Pepsi, and then 3 Fanta, for example. Okay, so we will select 3. The payout are, or in this game, they give you money. Okay, the payout are $10 if all 3 that you select are black. Okay, you get the payout is $10 if all black, $20 if all blue, and $30 if all red. This is all blue, and then $30 for all black. I'm sorry, all red. Okay, those are the payout. Implicitly, there's one more payout that they don't list here, but it's consequently part of the payout. What happens if you don't get any one of these events? Like, what happens if you select these markers? You get a mixture, let's say some black, some blue, or some black, some red, or some blue, some red, or maybe one for each. Then what do you get? Implicitly, you get nothing, right? Okay, so these are the payout. These are the payout. Now, the question is then, we need to compute the probability distribution for the payout. So we need to create this. We need to create the probability distribution for the payout. Okay. Let's call that x. Let x be the payout. But X here has to be numerical, okay? It has to be value, right? Okay, so probability that the payout is $10, the probability the payout is $20, the probability payout is $30, probability the payout is nothing. So what is the probability? Now let's compute it here. Probability that the payout is 10 means you have 5 black and 7 not black, right? You need to get 3 from here and nothing from here. What's the probability? That will be 5 choose 3 times 7 choose 0 over 12 choose 3. Okay, and then you compute that. That will be 10 times 1 over, what is this? 220. So that will be 10 over 220. And then you do that again for probability x equals to 20, probability x equals to 30. Okay, the way we basically did it before, okay, the way we did it here, okay, if you think about it, okay, keep them in fraction, and reduce with common factor at the end. Okay, I will ask you to do that later, but I want you to realize one thing. There's another way actually to compute this probability of the payout is 10. The probability that the payout is 10 is the same event when you get all black, all 3 black, right? Now, because all of them the same color, then it doesn't matter the order as long as all of them black, right? So you can actually do it one by one. Probably the first one is black is 5 over 12. The second one is black is 4 over 11. The third one is black is 3 over 10. And you will see that it simplifies to the same number. That is 1 over 22, which is the case if you reduce this fraction. If you reduce that fraction, you get the same 1 over 22. Okay. Now, if you ask me how will I do this problem, I have a tendency to do it either way. There's no preference in this case because all of them black. You will not be able to do it this method if I say the payout is $15 if you get 2 black and then 1 red, for example. 2 black and then 1 red, then you get a different payout, for example, then you cannot do it this way anymore. Why? Because when you do it this way, let's say you do black first and then black second and then red, you are working in this kind of order. While when I said what I said earlier, 2 black and 1 red, I didn't imply the order is important. I didn't imply that the order is important. But in this case, or if we go back to this question, you will see probability of all black can actually be computed using fundamental theorem of counting method. Just do it one by one. Okay. Now, I will give myself a little break. Let's say 5 minutes break. I would like you to do this. Okay. Fill this up. Okay. Find that out. And then put it in here. Okay. Now, then how do we find these terms? You know the total has to be 1. Right? You know the total has to be 1. So once you get this guy, this guy, this guy, subtract the sum from 1, you will get this guy. Okay, now let me give you maybe 5 minutes for that. If you are not done in 5 minutes, don't worry. It's not a quiz anyway, it's not a test. Okay, let me take a little break. Sorry, I forgot to record this. Go on. I did the probability, the payout is 20, payout is 30 there. And then once we put these three probabilities here, then of course, I hope at that time you realize that the total is not 1, and there's some payout that we don't list them yet, and that is the event where the payout is 0. Now, there are so many possible events where the payout is 0. So instead of computing them one by one, we just see, oh, the total has to be 1, right? If the total has to be 1, then I do this kind of computation, 1 minus the sum here, okay, to get the remaining probability with payout 0. Now, in the past, there were times, so it could be also in your test later on. I will ask the students to go further, computing the expected value. That's possible. Okay, it is possible that I may ask you to go on, extend this to find the expected value. Now, the thing is, I would like to ask you first, suppose you go to a county fair or a city fair. I live in Monterey Park. So like in the last many years, except this year, they usually have a fair, like Lunar New Year, okay, on Garfield, and they do the spin. Some vendors actually do the spinning, and then you get some money or some reward if you happen to spin to a correct place. Okay. Now the thing is, you do it without paying. You do it without paying. That's a nice thing. Okay. Such that if you think about it, actually you don't need to think too hard. You see that if I offer you this kind of game, in your leisure time, in your free time, okay, will you play this game? Yesterday when I asked that, not yesterday, 2 days ago when I asked that question to my other class, I have actually plenty of students say, no, I will not play it. I say, why? Because the probability of getting some money is so low. It is true though. The probability to get $10 is actually less than 5%. Okay, not to say $20, to say $30. Okay, but will you play this game if you have time? The answer is supposed to be yes. Why? Because you lose nothing. You don't need to pay for this game. So the expected value should be positive, right? You can try extend this later on. You extend this px, right, and then compute this. You will see the expectation for you will be a positive number. Okay, which means in the long run you will win that money on average. Okay, let's just extend it here, but I will use different color because it's not part of the answer for the problem here. So let's say I extend it using the green color. Okay, so px, this is 100 over 220. This is 80 over 220, 30 over 220, and 0. So when I add this, I get 210 over 220. So the expected value, the expected payout is 210 over 220, which is 0.95454545, and you round it to 5 decimal places. Now, what does this mean? What does this mean? This means in long run, that's the expectation, right? So in long run, the average payout is $0.95455 per game. Okay, so I as a player, I can play it maybe 100 times, right? But when I played 100 times, on average, if I played 100 times, I will win around 95 cents per game. Multiply that by 100. Then on average, I will win $95, 45 cents, 46 cents, right? If I play 100 times, if I 100 times play 100 times, then we expect to win 100 times 0.95455. That's $95 or 55. Okay. Now, the thing is, if a game has a positive, a non-zero expected value, if the expected value is non-zero, then that game is not a fair game. Okay. For a game to be fair, the output has to be zero. Okay, the expected value has to be zero. So you see that if you go to a fair and you see a vendor doing this kind of game, they just try to be nice with you. Okay, they try to make the fair to be more joyful, more cheerful. Like people go home thinking that they win something. Okay, at least they have a joy of trying, even though they don't win anything. But we give them some hope. So when they go home, they feel happy. Oh, you know what? I spin the wheel. Oh, I almost get the $30 one. You know, okay. But this is not something they will do every day as an income, because the expectation for the party or the vendor doing this is negative. It is positive for the player, right? For the player is positive. So for the vendor or for the dealer in casino sense, this is not a winning game for them. Okay. So how to make it fair? How to make it fair? Then the vendor, if they want to make it a fair game, then the vendor will ask you to pay this much to enter the game to make it fair. Whatever the expected value, that's how much the vendor or the party, the dealer will ask you to pay to enter the game. Now, of course, you won't see this in casino. Why? Casino is in business to make money from you. Okay, so do not think that casino is ATM. You go there, you make money. No, no. Okay, for some people maybe that's the case, but in general, that's not the case. Okay, you can easily find people going to casino and coming out from casino actually winning money. You can easily find. Okay, that's not unusual. Okay, but it is even more often people coming out from casino losing money. Okay, so how to say? Do not think it's like the probability for you coming out from casino with more money in your pocket, let's say only 10%. Well, is it rare? No, it's not rare. Is it unusual? No, it's not unusual. It's more than 5%, right? So it's not unusual. Okay, but do not think that because it is not unusual, then other event of losing money, for example, is rare. No, I'm not saying that. We say that making money by going to casino is not unusual because the probability is more than 5%, but it's not majority because the probability is a lot less than 50%. Okay, casino in their registration for doing business actually categorize themselves as entertainment business. So you go there, they entertain you, of course, through gambling. Okay, but they make money from you. So at least I expect if you see this kind of game in casino, they may charge you at least $1 for this game. They charge you $1 for this game, such that all of a sudden the expected value for each player becomes negative, as we expect. Okay, as we expect, that's what we want. So that's what will happen. And I also think we saw that also last week when we went over problems from the textbook, right? That when you go to casino, you do expect to lose some money. Is it for this class or the other class? I don't really remember. Well, anyway, uh, if the expected value is not zero, then it's not fair. If you want to make it fair, then the vendor will charge this amount of money for you to pay. Now, because this number is ugly number, okay, and casino, if this is in casino, then they will take advantage of this ugly number and charge you slightly more with a better number, let's say $1. Okay, let's go on. The last problems for this before we go back to 5.2. Question number 2. Mega Million Lottery draws 5 regular number out of 75 numbers. So we have 2 boxes. One of the regular. There are 75 regular numbers. Okay, 5 of them correct. Okay, therefore the other 75 is wrong. Okay, and then from another box called Mega Box, okay, mega number, there are 15 numbers there. You need to select one of them, so only one of them correct, and the other 14 is wrong. Now, the question is, find the probability of correctly select none of these all 6. So you select 6 numbers, 5 from this group, 15 from this group, but all of them wrong. So the 5 that you select must be from the wrong one, and the one you select in the mega has to be from the wrong one. What will the probability be? Now there will be, well, from regular one here, I select nothing from here, and then 5 from here. For the mega one, it has to be wrong, so this is nothing from here, 1 from here. So what's the probability? From this group, it will be 5 choose 0 times 70 choose 5 over 75 choose 5. That's the probability of getting all wrong for the regular part times probability for this event to happen. Okay, that would be 1 choose 0 times 14 choose 1 over 15 choose 1. That's the probability. And then from there, if you want to make it decimal, go for it. But here I specifically say don't need to compute the decimal. Just use the notation. So this notation is good enough. Okay, when you compute this, you will get the probability. Okay, one of the reasons I told you just use notation and don't compute it to decimal, because when you compute this, it may be very, very small. I mean, I don't know. It could be so small such that if you make it decimal, it's basically 0 if you only to 5 decimal places. Okay, the notation will show me how you think and how you process this information. Okay, now go on. How about part B? What is the probability of correctly select 4 regular numbers only? So for the regular one, you select 4 of them correctly. If 4 out of 5 is correct, means one of them that you select must be wrong. Okay, now likewise for the mega part, it has to be wrong also, right? Because the one correct only 4 regular numbers. So if 4 regular correct, 1 of the regular wrong, and the 1 for mega has to be wrong also. Then the probability will be 5 choose 4 times 70 choose 1 over 75 choose 5 times, from the mega box, 1 choose 0 times 14 choose 1 over 15 choose 1. And I will just leave it like that. Okay, I will just leave it like that. Now, right now it's approximately 10 o'clock. I would like you to take a little break. Okay. Earlier I took my 5 minutes break, basically taking some breath here while I asked you to work on this problem, right? Remember? Okay, but this time I give you a break, 10 minutes break. We come back at, make it a nice number, at 10:10. Okay, I'm about to start 5.2, which is binomial distribution. 5.2 binomial distribution. Or binomial probability distribution. And this will take us approximately 1 hour 45 minutes from here. But before I really go over this binomial probability distribution, let me talk a little bit about your test. I finished grading half of yours already, not finished all of yours yet, but I expect that you should be able to have the test back uh, most likely by tomorrow morning. Okay, I have to work it out in the evening. In fact, in the midnight, because during the days I can only work when my son and my daughter are sleeping. Okay, but in case you want to know how I return your test back to you, I have some students to ask me that question. Let me bring your attention to a sample student. I use this is not a student from in the class. This is a test student. How to say it's test student? So in my list, let's say in my list. Okay, I have the college actually give one test student. Okay, so assume that this student is actually an actual student. This is not an actual student. No, this is just like kind of like a phony student that I can use to show you in class or how things actually work. Okay, now let's see. I want to show you where I put your return test. So from your point of view will be like this. Okay, okay, and then you can go to, for example, test 1. See if there's any comment here. See if there's any comment here. Okay, see if there's any comment here. And when I return your test, it will be an attachment. So you give me PDF file, right? When you submit that in PDF file, then I will attach the graded test also in PDF file. You need to download it though for you to see. Okay, that's yours anyway. So you will have your own file where the one that you submit, and also the one that I grade later on as a comment here. Okay, that's for how you will see your return test. I think for your quiz, you can also see it already, right? Oh, by the way, before I forget, yesterday I post a very big quiz that's due next week. Okay, this is actually 5 quizzes put together. Quiz 7, 8, 9, 10, 11. Okay, 7, 8, 9 covers up to the one we did last week. 11, 10 up to the one we covered today. Okay, yeah. So basically this weekend you can finish this already. And once you finish this, you already seen the majority of the problem you expect to see in your test 2. Of course, similar problem. I'm not referring to exactly the same problem. Okay. Now let's come back to our class. Binomial probability distribution. Uh, uh, an experiment follows binomial distribution if it satisfies all 5 of these requirements. Our textbook says only 4, but there are actually 5. The first one, the number of trials is fixed. We denote the number of trials by lowercase n. Second, the outcome, there are only 2 outcomes for each trial. Now, our textbook, just like a lot of other textbooks, will call those 2 outcomes success or fail. Okay, but the key is actually there are 2 complementary outcomes, either success or fail. Now, it can be in other way open or closed. Everything binary or male female, boy girl. Okay. I know in reality, in our culture, in our society right now, when it comes to gender, a lot of people believe that it is a spectrum. Instead of a binary male and female, it's a spectrum. But in our course, just for sake of simplicity, okay, just for sake of simplicity, even our textbook actually use that kind of categoric binary category for gender, male, female, boy, girl. Okay, but it doesn't imply, I'm not trying to say that's the right one in our society. No, I'm not the judge of our society. I have my own view, you have your own view, but in public, I believe most people believe the gender is now in form of spectrum instead of binary. Okay, but in our class, following a lot of textbook, they still see gender as they still use gender in binary sense in example. Okay, so please don't take it as if that's what I believe to be correct. No, that's not in that sense. It's just for sake of simplicity, for sake of teaching you binomial distribution. Okay, male, female, yes or no, yes or no. What else? AM, PM. Okay, pass or fail. Not in sense of passing the class or failing the class. Well, you can use that also, but in sense of if a legislation being passed or failed to pass. Okay, and a lot of other things though, a lot of other things. Let's say, for example, a traffic light. Yes, traffic light supposed to have 3 outcomes, green, yellow, or red, okay? But in reality, it's either go or not go. It's either red or not red, right? Okay, yeah, I myself still see yellow as go. In fact, if you see yellow, go faster, right? But that's me though, that's me. But in this binomial probability distribution, basically we call that binomial because each outcome, each trial has only two possible outcomes. Okay, to be more precise, I think in middle run, maybe in 5-10 years, instead of calling that success or fail, our textbook may call that success or not success, because for example, in some case like yes and no, okay, it's not really binomial like that. Some people say yes, some people say no, some people say no opinion, for example, right? Okay, so in that case, we prefer to say yes or not yes. Okay, pass or not pass, male or not male, open or not open. Okay, to avoid the possible third or more categorical that is not covered in this binomial. Let's say for example, in case of male and female, we agree that some people is not actually both. Some people say no, I'm not 100% male, 100% female. Okay, and that's fine. That's fine. Okay, that's because what the way they view gender as a spectrum instead of binary. I hope you understand what I mean by binary. Like some people's view of gender right now is male or female. Now, when we say it's a spectrum, it means it can be anywhere in between. It can be anywhere in between. Okay, yeah, it can be anywhere in between. So to avoid that possible non-binary situation to apply into binomial, then in future there's a chance that we will categorize the gender as, for example, male or not male, like that. Okay, and then let the audience decide themselves on the spectrum, will they put themselves in male or not male, like that. Okay, but that's for the society though. Okay, in our class for now I will still use male female, but not in sense of that's what I believe. Okay, that's not what I believe. And even if that's what I believe, that's not what I enforce to you. Okay, that's not at all. Now, that's the third requirement, that each trial has only two outcomes. Okay, and then the probability of success denoted by lowercase p is constant throughout the experiment. And independent among trials. Now, before I finish this, the other two requirements, let me give you one example of binomial distribution. One example of binomial distribution is, for example, I toss a coin. Let's say 6 times. Okay, and then we want to observe the number of tail. Okay, now this 6 times is the number of trial. Okay, they fix it. Okay, we're gonna toss it 6 times. Okay, now when you toss a coin, there are only two possible outcomes for each trial, either head or tail. Then you put that in our list. Head or tail. Okay, and probability of getting a tail, for example, is constant throughout this experiment. Why? Because we use the same coin. Okay, we use the same coin. So the probability of getting tail right now, if you toss it first time, will be the same to the second time you toss it, the third time you toss it. And independent among trials means if the first time you toss it, you get tail, for example, it doesn't tell you anything. It's independent of influencing or increasing or decreasing probability of getting tails the second time. Just imagine if you toss a coin. If you toss a coin and you get a tail right now, does it tell you anything about what will happen in the next toss? No, it doesn't. Okay, that's why we say among the first trial, second trial, among all trials, the outcome of any trial is independent of the outcome of any other trial. Knowing the outcome of the first trial doesn't tell us anything in any way for the probability for the outcome in the second trial and others. Okay, next. The fourth one, what's that? We are interested in the number of successes regardless the order. So we are interested in how many tails occurring or show up if you toss this coin 6 times. Okay, and the last one is yeah, probability of success is, I happen to say that to actually change it to 4 then. I happen to say 2 of them in the same number, 4. Okay, the third one actually has 2. The first one is it's constant, probability of success is constant and independent among trials. Yeah, I happen to put them together. Constant throughout the experiment. So let's say probability of getting a tail is 60%, right? Then because we use the same coin, then probability of getting a tail will be 60% for any trial in that experiment. Okay, and it's also independent among trials. That's the experiment that gives us binomial distribution. Notation. Let X has let X be binomially distributed. With parameters n trials and probability for each success p. notation, then X will be distributed binomially and P. Random variable X is distributed binomially with number of trials and probability of success P. That's the notation. Now, you don't see this notation in the textbook, but I strongly suggest you to get used to this notation. Okay. For many reasons. One of them, especially, is because this notation summarizes what we need to worry. There are zillions of binomial distributions, but you will see every time you deal with binomial distribution, it only boils down to the number of trials, probability of each success before you go forward with computing probability. Okay, now if we look back into our small example earlier, then the notation for these will be the number of tails will be binomially distributed with number of trials 6. Now, they don't tell us what is the probability of getting a tail there, but let's say probability of getting a tail is 0.35. So the probability of getting each tail is 0.35. That's the notation. Now, for the next approximately half an hour, for the next approximately 20 to half an hour, we will first learn, again, the notation and the calculator punch, like how to use your calculator to compute binomial distribution. My assumption is you already have your TI-84. Okay, now suppose now I get the real example, example 1. Let X be binomially distributed with n equals to 6, the lowercase p is 0.35. Part A. Find the probability that X is equal to, let's say, 3. That's the probability notation. That's the probability notation. Now, from the probability notation, I need you to go to write down the calculator notation. And the calculator here refers to TI-84. 8384 has the same notation. That will be, it's binomial, right? It will be binom PDF. We use P if the binomial probability that we want to get is exactly equals to a certain number. Okay, binom PDF, parenthesis 6, 0.35, 3. That's 6.6, 0.35 from the NP, and the 3 comes from here. Okay, now let's see how to use our calculator for that. I will grab my TI-84. Now please, if you have your TI-84, also grab that. How to get that binom PDF? How to get that binom PDF? We go to second distribution. You see the blue one here? Above farce. Now, if you have actual calculator, usually that's yellow. They make it in yellow color. Okay, but you go second and then you click that farce, punch that farce. Okay, that's how you get to the distribution. Now, then you scroll down, you scroll down until you see binom PDF. That's binom PDF. Okay, Now, if you use TI-84, they usually guide you. Okay, they usually guide you with the notation. Like for the first number is the number of trial, that's 6. Enter. How about P? What is the probability of success in each trial? That's 0.35. Enter. How about the X value? The number of success you want to compute the probability. That's 3. And then paste. When you press paste here, then it will give you the notation. Okay, you see that binom PDF 6, 0.35, 3. Okay, now that's the one you need to put in as the calculator notation. Enter, that's the probability. Okay, 0.23549. That's 0.23549. Okay, so let's try another example. Suppose I want to find out what is the probability that x equals to 5. Then you do the calculator notation first. That will be binom PDF, the n, the p, and then the x. So for example, if I put the story into this example 1, let x be the number of tails observed when you toss a coin. 6 times probability of tail is 0.35. Then what is the probability when you toss this coin 6 times, 5 of them tail? Okay, that's the probability notation. And then calculator notation. Now let's compute what is the number. So I get second distribution, go to binom PDF, number of trials 6, probability of success 0.35, the x value is 5, enter, and then paste it. Okay, now then you will see the calculator notation, right? You will see the calculator notation. Then when you press enter from there, you will get the probability of getting 5 tails. When you toss it 6 times, 5 of them tail is 0.02048. 0.02048. Okay. Now, part C. What is the probability that x is at most 3? At most 3. Now, notice the following. When I toss this coin 6 times, there are actually 7 possible outcomes for the number of tails. It is possible you don't have any tail, maybe only 1. Maybe you get 2 tails, or 2 tails, 3 tails, 4 tails, 5 tails, or 6 tails. Okay. Now, in part A, we want to find out what is the probability to get 3 tails. That's for part A. For part B, we want to find what is the probability to get 5 tails. Now, part C, however, is the probability to get at most 3 tails. Okay, so the probability here is actually the same to us. What is the probability to get no tail plus probability to get 1 tail plus probability to get 2 tails plus probability to get 3 tails. That's what we're supposed to compute. Now the problem is if you want to do it one by one, they will take a lot of calculator notation and a lot of rounding errors. So instead of computing it that way, we will use calculator right away. Okay, it has this function on our calculator called binom CDF. The C there stands for cumulative. Cumulative. Now, I hope you understand what the word cumulative means. It means up to. Okay, in this case, it's up to 3, including 3. Now, the calculator notation will be binom CDF and P cumulative up to 3. Okay, so the first two numbers, the first two entries are the same. Okay, and then the last entry is what it is up to. Now, you can try using your calculator. The position for binom CDF is right below binom PDF. Right below binom PDF. So if I use my calculator here, is it on here? I will see my calculator, right? Okay, so second, parse, scroll down. You see binom CDF here? Okay, enter the number of trials 6, enter probability of success for each trial is 0.35, enter cumulative up to 3 tails, enter, paste it, and then when you enter again, you get the probability. 0.88258. 0.88258. Okay. Now part D. I make a similar question. Find the probability of the number of tails is at most, let's say at most 5. Probability that the number of tails will be at most 5. So it's basically from 0 to 5, right? That will be binom CDF 6, 0.35 up to 5. Okay, now let's do the calculator. That will be second distribution. Now I want to start teaching you some trick. You know that binom CDF is quite far at the bottom of the list. So instead of going down, you can go up. So you start from the bottom of the list. You see that? I go up, you start from the bottom of the list, and then go up, 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 up. Now you see binom CDF, right? And then enter. And I get 6 there, 0.35, cumulative up to 5. Enter. Cool. I get 0.99816. 0.99816. Now suppose you want to find out what is the probability that x at most 3, right? Let's say I want to compute part C again. Okay, but notice that part C and part D are the same function. They have to be the same function, same two numbers, except this one here. If you want to change one entry, on your calculator, okay, you can do the following. You get the entry here. Do you see this entry? Not enter, entry. On your calculator, there should be the blue one. I'm sorry, the yellow one. Now, so if I want to change that entry, 5 becomes 3, I go second entry. It will copy that down for me, and then you go back, change this to 3. Boom, boom. Okay? So you remember that I have part C, right? I have part C. I just need to change to get to answer part D. I just need to change that 3 becomes 5. Then I use the result I have from part C. But now I change the cumulative up to 5. See, it's a lot faster, right? But that's a little trick for your calculator though. It applies for my online calculator. Okay, but I know when I use on my TI-83 Plus, it also works. Okay, now let me go on. Two more variations. First one, what is the probability that x is less than 3, for example? The number of tails is less than 3. Not up to 3, but less than 3. Now, if you take a look, the possible outcomes are 0, 1, 2, 3, 4, 5, 6. Now, when we say less than 3, it means only up to 2, right? Only up to 2. So do the adjustment first for the probability notation. This is probability that x up to 2. Do that adjustment first. And then you do calculator notation, binom, CDF, 6, 0.352. Does it make sense for you? Then I grab my calculator. That's exactly the same to the previous entry, except that I need to change the 5 becomes 2. So binom CDF already, 5 becomes 2. That will be 64709. 0.64709. So if you have less than, the phrase less than means, well, less than. It's not up to, okay? Less than means anything less than 3, only up to 2, not including 3. So if you have that situation, rewrite that probability notation before you write the calculator notation and answer it. Okay, rewrite it first. Thomas, will you penalize me if I don't rewrite the probability notation? Will you penalize me if I don't write this, Thomas? No, I don't penalize you for not writing that probability notation. But of 20 students I saw skipping this green step here, of 20 of them, 19 of them actually get this wrong. In other words, if the reason you skip this, you skip this intermediate step here, the reason you skip that one is very likely because you don't really see the need of rewriting it, and therefore you won't see how it will change the way you type it into your calculator. Okay? So if you take my advice, if you value my advice is rewrite the probability notation. Okay? For the less than case, for less than equal case, you can just apply the calculator right away. But for less than case, you need to do adjustment first. Okay? Now, last one, I will give you 2 examples for the next. What is the probability that x is at least, let's say, 4? What is the probability that x is at least 4? Now you look at the possible outcomes. Now we don't have calculator to compute that at least 4. 0, 1, 2, 3, 4, 5, 6. When we say at least 4, it refers to 4, 5, 6. But we don't have calculator to compute 4, 5, 6. Our cumulative always start from 0. That's why we call that cumulative. Okay, start from the very beginning. Like somebody asked me this, Thomas, will our final be cumulative? Okay, will our final be cumulative? And yes, your final will be cumulative. But what does the word cumulative means in that question? Well, cumulative means from the beginning up to, right? From the beginning up to. Our calculator can only compute cumulative. So what we plan to do is we will compute the complement and subtract that from 1. In other words, this is equal to 1 minus the probability of the complementary effect. 1 minus probability that x is at most 3. How do you get that at most 3, Thomas? From that diagram. From that diagram. AKA, in other words, for you to do this, I strongly suggest you to sketch this diagram first. Okay? To sketch that diagram first. That's what I recommend. Can I skip that sketching the diagram, Thomas? Yes. In fact, in the past, like around 10 years ago to around 7 years ago, I really thought this this way here without sketching the graph, until I saw a student doing it this way and always get it right. That student is not a bright student. Okay, that student is not a bright student, and that's why I think, oh wow, how can these students usually get it wrong for this type of question, ends up getting it right all the time? And then he say, oh, you know what, Thomas, I try to picture it this way. I can see it better. Okay, and learning from that student's very strong point, even though he is not considered a smart student, but in my opinion, this way to visualize that is actually a smart move, and that's how I adopt learning from that student's strong point method to get it right. Okay, to visualize that, I bring it to class. So if you ask me, sketch this diagram here. Okay, it is very helpful. It is very, very helpful. Okay, now remember, like a lot of people say, Thomas, I'm a visual learner, audio visual learner. I need to be able to visualize that. But the thing is, the same student who say that they need to visualize that, when they do problem, they themselves do not try to visualize it. So tell me, what you say is actually contradictory to what you do. Okay. Some students say to me that they are audiovisual learner, as if I am not. I am an audiovisual learner too. In fact, I'm a visual teacher. The thing is, because I sketch or do the graph for you, sketch the diagram for you, okay, it means I want you to do the diagram on your own also during the quiz or the test. Now, these same students who say that they are audiovisual learner, when it comes to test, they skip all the steps. Strangely, all of the sudden in the test, they are not audiovisual learner anymore. Okay, as if I'm dealing with two different people. In class, as a student, they are audiovisual. In tests, as a test taker, all of the sudden they can skip all the steps and get all wrong. Yeah, right. Right? If visualization is your strong point, then do it, graph it, visualize that. Okay, at least on the first day you learn it this way. Okay, please do that. Okay, this is for you though, not for me. This is for you, not for me. Okay. I hate it when It sounds like a hate speech. It's not. I hate it when I teach you this way and you try to use another way and get it wrong. I feel sorry for you. The worst part is students who say that they want to visualize that, they really try to visualize that without they themselves visually draw it and then get it wrong. The worst part is if you leave it blank, right? Okay. Some students' work is hard to grade. Okay. Most students' work is easy to grade in your test one. Why I say it's easy? Either you get it right all the time, or most of the time, your handwriting is easy to read, or you don't write anything. You just leave it blank. That's easy to grade also. Okay. Of course, that's not something I would like to get, right? But if you leave it blank, it suddenly becomes easy for me to grade, right? How about you write something, who knows, by you writing it, you start to get some good visualization. Okay, so please take my advice. Okay, please take my advice. Okay. At least for the first day of class today, you know, first time you see this, you encounter this, try to sketch that. Okay, now let me try to ask you this. Find the probability. Oh, you know what? I'm not done yet. This is 1 minus binom CDF 0.354, which we happen to compute already in part C at 0.88258. That's 0.11742. How about probability that x is greater than 2, for example? Greater than 2, not including 2. Greater than 2, but not including 2. So on my diagram, the possible outcomes are 0, 1, 2, 3, 4, 5, 6. When we say greater than 2, means it starts from 3. Now, the complement is up to 2. The complement is up to 2. So let me rewrite this. This is 1 minus probability that x is up to 2. That's 1 minus binom CDF 0.35, comma 2. Then I use my calculator. What's that? Binom CDF. Oops, that's Poisson. Binom CDF. Number of tries is 6. Probably 6 is 0.35. Up to 2. Then change this one. Enter, enter. So that's 1 minus 64709. 64. Oh, I have it up there. Yeah. Part E. That's in part E. 1 minus 0.64749. That is 0.3529. Okay. Now I'm about to ask you to do a similar problem. Okay, but I need you to write the calculator notation and then compute that using your calculator TI-84 or 83. Okay, example 2. Let x be binomially distributed. Number of trials is 10. Probability of each success is 0.57. I want you to compute probability that x equals to 7. Part B, probability that x equals to 4. Part C, probability that x is less than equals to 6. Part D, probability that x is less than 8, part E, probability that x is at least 4, and part F, probability that x is more than 5. Okay, let me give you 1, 2, 3, 4, 5, 6, 7, 8, 9, maybe 10 minutes from now. Okay, please do this. Please do this. So we come back, we will start discussing this at 10, 11, 10. Now, this is not a break for you. This is not a break for you. Can you quickly re-explain why for part G is 1 minus less than or equal to 2? Well, from the picture. So when we have greater than 2, it means it starts from 3, right? It starts from 3. Greater than 2 means it starts from 3. Now, then from the set of the possible outcomes, okay, greater than 2 implies 3, 4, 5, 6. Okay, so the complement of 3, 4, 5, 6 is up to 2. It's 1 minus probability x up to 2. That's the reason. Okay, that's why it becomes very crucial for you to get this diagram first. Okay. Again, let me give you approximately 10 minutes to do this problem. Okay, binomial distribution probability x equals to 7 is the calculator notation first, binom PDF 10 0.577. And I use my calculator 10 0.577. I get 0.18651. Now I may go too fast if you don't slow me down. So let me know if I happen to get it wrong, or maybe what you get is different from mine. Okay. Now part B, the probability that the number of successes equals to 4. Binom PDF 10 0.574. I get 0.14013. Probability number of successes at most 6. Probability x is up to 6. That's binom CDF. Okay, so if it is exactly equal to, you use PDF. If it is up to, you use CDF. Okay, and I have 10 0.576. I get 0.68984. Now, probability that the number of successes is less than 8 means I need to do adjustment first, means only up to 7. Okay, And then this would be binom CDF 10 0.57 not 6 7 up to 7. Binom CDF 10 comma 0.57 comma up to 7, that's 0.87635. Okay, now then part E. Probability number of successes is at least 4. Oh, let me do the diagram first. At least 4. So starting from 4 and on up to 10. That's what we need, the probability of at least 4. But then the complement means it's up to 3. Right? Okay, that's 1 minus probability that x is up to 3. That's 1 minus binom CDF 10 0.573. 1 minus 0.08058. That's 0.91942. Okay, then that's equal to more than 5. Probability that x is more than 5. Let me use the plot here. 5, 6 to 10. But more than 5 means start from 6. Right? The complement is up to 5. So this is 1 minus probability that x is up to 5. It's 1 minus binom CDF 10 0.575. I get 0.44361. 0.55639. Okay. By the way, do you realize that binomial distribution is heavily used in this election, especially if it is properly used? It should be used in a state instead of the whole United States. What I'm saying is this. Okay, suppose, for example, we want to find out if this little example. Okay, please see this from probability statistic point of view, not from political point of view. Okay, but you know, it's something quite relevant. Suppose we say in California, let's say I make up numbers. Okay, let's say 63% of voters Democrat leaning. Democrat leaning. In other words, if they vote, then they will vote for example, the president from Democratic Party. Okay. Now the thing is, not all voters going to vote. Okay? Not all voters going to vote. So let's see, if there are, let's say, I just make up numbers, okay? If there are, let's say, 300 people, California people voting, then find the probability that the majority will vote for Democrat candidate. Now, when we say the majority means more than half. That's more than half. Right? Okay, more than half. So solution, let X be the number of people who will vote for Democrat candidate. It is binomial. The number of trials 300. Probability each person, each voter vote for Democrat will be 0.63. And find the probability that the number of people voting for Democrat candidate is, it has to be more than half, means it's greater than 150. It has to be greater than 150. It's majority, right? More than half. Not including 150, no, it's more than 150. Then you see this is equals to 1 minus probability that X is less than equals to 150. Right? So if you suppose you use the table, the diagram, okay, 150. When we say more than 150, it means it starts from 151. Right? The complement is up to 150. Okay, now then you use your calculator. This is binom CDF 300, 0.63, 150. I get 1 minus 0.00000297.5. The number I get from calculator is 2.975 blah 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 e negative 6. That's from calculator. But in scientific notation, it means 2.975 something times 10 to the negative 6, which implies the 2 here, which implies the 2 is at the 6 decimal place. Okay, which when I subtract, I will get 0.999997025. So the probability that the majority will vote for Democrat candidates is nearly 1. If I round to 5 decimal places, that would be 1. So is it possible that, for example, California, and you know this number is hypothetical, okay? I just make up numbers, okay? If you have the voters are 63% Democrat leaning, then the probability of 300 actual voters to have a majority vote for Democrat candidates will be such a high probability. Okay. Now, if you give me a chance, maybe I hope next week or 2 weeks later, I think next week, I will do what we call Bayes' theorem, okay, to explain the following situation. Okay, in California, for example, we know California is Democrat leaning. However, this number is not as high anymore. This number is not as high anymore. As I know, this number is now around 57%. Not 63, it's around 57. Still, because the population size in California is so high, like millions of voters, right? So the probability that California ends up, majority ends up voting for Democrat candidate will be nearly 1, okay? Now, but please don't slack off, okay? Regardless which candidate you are voting for personally, okay? If you don't go to vote, your vote don't count. This is true regardless your political preference. Okay, so regardless what is your political preference, I, as another citizen of this great country, I want you to go to vote. Okay, vote for your future, vote for your next generations, what they will get. Because of course, at least for the next 4 years, whatever you choose right now, you vote for right now, will affect what will happen, at least in the next 4 years, maybe more. Okay? So regardless who you will vote for, please go to vote. Okay? I usually say this to my friends who say that, you know what? It is true though, it is true. California basically Democrat leaning. So regardless who you vote for, California votes, electoral college will go to Democrat. It is true. It is true. So even if Thomas, one person not going to vote, it will still, the electoral college will still go to Democrat. The problem is if you have too many people like me who think, for example, I will vote for Democrat, for example, and I think, yeah, you know what, it will be for Democrat anyway. So I don't go to vote because I think that Democrat will carry California anyway. Now, if you have too many people like Thomas, then don't blame other people if, for some strange reason, California is stolen to Republican. Why? Don't blame it on them. Blame it on those Democrat lazy ass. I'm sorry, but yeah. Okay. So regardless what the polls say, okay, regardless what the polls say, the polls say 63%, but if plenty of these 63% who say they will vote for Democrat candidate not going to vote, then their vote don't count. If poll can be used as a foundation for who will win the presidency, then there's no need for us to actually go to vote, right? Just do the poll. But no, poll is only to give us the glimpse of what will happen later. Okay? And next week, I will explain to you what happened to, how many years ago? So it's 12 years ago. The case of George Bush and John Kerry. Okay, what happened at that time? Okay, but please vote. Whoever you want to vote, it's up to you, of course, right? But I usually say to my friend, if you don't go to vote, then STFU. You don't go to vote, you have no right to complain. Okay, of course, that's harsh though. In fact, to be honest with you, I have to say the right to vote is also means the right not to vote, which I still have to respect actually, right? Okay, but at the same time, if you don't go to vote, then you waive your right to say anything about the outcome later on. Okay, in fact, even if the outcome is not what we want, we still have to accept it though. Okay, we all pray for a fair election, of course. That's the most important one. That's example 3. We will start working on problems from our textbook. Let me grab my textbook and pick problems from there. We will work on, we will do problems from our textbook. And of course, we will attack word problems. This is when what we learned before, just the notation and calculator notation, now being brought up to translating from word problems into probability notation and therefore calculator notation. Okay, now let's see, let me quote some problems from our textbook. Let's say pick question number 8. This, I think this one is a fun question. No. From our textbook. I would like number 14. Let me quote number 14. Give me a second. Okay, number 14, we have this. The question is cut between 2 pages, so I need to copy paste the others, the rest. So based on data from a Harris Interactive survey, 40% of adults say that they prefer to get their news online. Now, 4 adults are selected. So we will have now X is binomially distributed. The number of trials is 4. Probability of each success is 40%. Okay, where X is the number of adults prefer to get the news online. Okay, now part A, we will see the internal building block of binomial distribution. Use multiplication rule to find the probability that the first 3 prefer to get their news online and the 4th prefers different source. So it's basically part A to find the probability that the first 3 is online and the last one is from different source. The first 3 is online, it's 0.4 times 0.4 times 0.4 times, to get a different source, it's 0.6, the complement. Okay? Now, if I compute this, that's 0.4 cubed times 0.6, I get 0.0384. Now, the thing is, to get 3 prefer to get it online, it's not only this order. Okay? To get 3 online, prefer to get their news online, have different arrangement. One of them is something we already computed. Okay, but there's another, there are actually 3 others way. Online, difference, online, different, online. There are actually 4 ways in total to get 3 onlines and 1 different source. Now, how do we know that there are 4 ways? It comes from 4 combination 3. That's how we get that 4. Okay. Now the thing is, the probability to get online difference is equals to probability online different online equals to the probability of online different online equals to probability of different online. Each one of them is 0.0384. So what is the probability of getting 3 onlines, which implies 1 different? That is 4 combination 3 times 0.4 cubed times 0.6. Okay, this is the internal work of how we compute it supposedly. Okay, but right now, because we have TI-84, this is basically binom PDF, number of trials 4, probability of each success is 0.4, and the number of desired success is 3. Okay, so instead of punching 4 combination 3 times 0.4 to the power of 3 times 0.6, TI-84 make it simple for us to compute it this way. Okay, now then what happened is this then. If you look at my solution from, I think from prior to 3 years ago, so in the past, I told my students to just use TI-30 because TI-84 was too expensive at that time. So I asked them, you know what, just use the TI-30. That's cheap enough. Okay, then along the time, more and more TI-83, TI-84 available in the market as the used calculators. So you can get it cheaper online once it goes down to around $50, $60, you know, for the used one. Then I start telling students, you know what, I need you to get TI-83 or 84. Now, starting last year, I require my students to use only TI-84. Most students coming to my class at that time already have TI-84 instead. So I told them, and then just use TI-84. Even if you need to buy it, you can get it online quite cheap. You don't need to buy it right away in the first 2 weeks. You can wait until week number 3 when it gets cheaper. Then you buy it online from eBay. Okay. Now, of course, some students say, Thomas, I don't have money right now. It's too expensive for me. Then you still need to get it somewhere else. And one way is actually to get it from, you can use that, what you call that, emulator, TI-84 emulator on your computer. Okay, but this is the internal work of binomial distribution. Okay, let's go on further. This time I use a question from number 21 to 24. From number 21 to number 24. Assume that when adults with smartphones are randomly selected, 54% use them in meetings or classes. Now, this is based on data from an LG smartphone survey. Number 22. Number 22. So here we get the P is 54%, or in decimal, that's 0.54. Change it to decimal before you plug that into calculator. Or you can also use fraction, but definitely not percentage when you use your calculator. In number 22, if 20 adult smartphone users are randomly selected, that's our N. Find the probability that exactly 15 of them, 15 of these 20, use their smartphone in meetings or classes. So probability notation, probability X equals to 15, right? Where X is binomially distributed, N equals to 20, the P is 0.54. So then this is equals to binom PDF 20, 0.54, 15. Okay. So we have learned how to come from here to here and then to get that. We have learned how to come from the probability notation to calculator notation to the solution. What we learn from this question is to move from the word problem to the probability notation. That's what we learn at this point. Okay, so can you summarize and therefore analyze from the passage, from the word problems, and formalize the probability notation? Once you get the probability notation, you can go on from there, because we already trained ourselves to come from probability notation to calculator notation and get the answer. Okay, now how about number 24? Number 24, if 12 adult smartphone users are randomly selected, which means in number 24, our N is 12. Therefore, my X is now binomially distributed. The N is 12, probability of each success is 0.54. The question is, find the probability that fewer than 3 use smartphone in meetings and or classes. So fewer than, probability that X is fewer than 3. Okay, not including 3. Fewer than 3 means less than 3. So then we adjust this to less than 3 means up to 2. Okay. Now that's, once you know the probability notation, then you should be okay with the rest of the steps. Okay. Before I go on, let me do one more thing. I think I should write it above there. Yeah, let me just do it here, so that when you restudy from your notes, you don't see it in two different places. Now, if you have binomial distribution with parameters NP, then the expected value, which is the mu, is given by N times P. Again, only if it is binomially distributed. And then the variance is NPQ, where the Q is the probability of failure, 1 minus P. You need to memorize this. The mean is N times P. The variance is NPQ. Now, let's scroll down. So for example, number 24 here, if I ask the mu instead, there will be 12 times 0.54. That is 6.48. And the variance is n times p times q. That is 2.9808. Now, the standard deviation, therefore, is the square root of that number. That gives me 1.72650. Okay, now from here we are actually ready to do problems from our textbook. At least I did one example already. Let me see. Number 20, maybe I use number 28. Number 28. Based on a Harris poll, among adults who regret getting tattoos, 20% say that they were too young when they got their tattoos. So we actually have the starting point is people who regret. Now, of those who regret, 20% say that was because they were too young. Now, assume that 5 adults who regret getting tattoos are randomly selected. Part A, so the n equals to 5. The probability they regret and getting it too when they were too young is 20%. Okay, let X be the number of people getting tattoos too young. So our X is binomial distributed. Number of tries is 5. Probability of success, in other words, probability they get it when they were too young is 0.2. Now, what I want you to do is to compute part A, part B, part C. And part C. Let me see if there's other question we can use to do this. Later on. Let's do this one first. Hey, you know what? Let me just put it right here. Number 30. Number 30A. You actually have your textbook, so you can see from your textbook number 30A yourself. Okay, let me leave it like this. So I want you to do this A number 28 ABC and number 38. Now, number 38 basically asking you what is the mu x and what is the standard deviation. Now, but I need to modify part B and C. What I want you to get for part B is find the usual interval. Usual interval as defined before is mu minus twice standard deviation. Mu minus twice standard deviation up to mu plus twice standard deviation. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 plus 20 minutes break. The long break. We come back at 12:20. We come back at 12:20. And then at 12:20, we will summarize this section here. At 12:20, we will summarize this section. Okay, you can take your break first and then work on this, or you can work on this first, then take your break. Part A. So we have 5. The number of tries is 5. Probability of success is 20%. Part A. Find the probability that none of selected adults say they were too young to get tattoos. So probability that x equals to 0 equals to binom PDF 5, 0.20. The probability that none of them get tattoos when they were too young. That's 5.20. That's 0.32768. Part B, probability that exactly one of these 5 says that he or she was too young to get tattoos. That binom PDF 5021. I get 0.4096. Part C, find the probability that the number of selected adults say they were too young is 0 or 1. Probability that x equals to 0 or x equals to 1. Now you can do this as probability of x equals to 0 plus probability that x equals to 1. Both of them already computed in part A and B. That's one way to do this. So I wonder what's that. I get 0.73728. But that's one way to do it. If you think about this, this is the same, the events that they asked for here is the same event to probability that x is at most 1. Right? That is probable binom CDF 5, 0.21. That's one way to do it. That's equals to 1. Let's see. Well, let's say we expect that 0.73728. Now then, part D, which I didn't ask you to do, is one a significantly low number who say they were too young to get tattoos? Is the output 1 significantly low? And because it's more than 5%, the answer is no, it's not significantly low. Okay, because the probability is more than 5%. Now, to be more precise, the way to compute this part D, should be done in the following way. We find the better way to answer that question is by looking at the usual interval. Okay, the usual interval is you need to first find the mean, which is 5 times 0.2, that's equals to 1. The variance is 5 times 0.2 times 0.8, that's 0.8. And therefore the standard deviation is square root of 0.8, that's almost 9. 0.89443. Now then, from there, you build your usual interval. That's 1 minus 2 times 0.89443 up to 1 plus 2.2 times 0.89443. Then from there you will see is 1 in this interval. This is negative 0.78885 up to 2.78885. So instead of saying that 1 is significantly low or significantly high, we see that instead 3, 4, 5, 3 and 4 and 5 are not in this usual interval. Okay, now we say that that outcome is significantly low. If it is significantly low, then that outcome is to the left of this smaller than lower fence. We say that outcome is significantly high if it is greater than the upper fence of the usual interval. Okay, so remember that I said before that the way we define our usual interval in this class is consistently by doing the mean minus twice standard deviation, the mean plus twice standard deviation. Okay, I did mention around 1 month ago saying that the usual interval may also be done by the first quartile minus 1.5 interquartile range up to the third quartile plus 1.5 interquartile range. Okay, the result usually the same. Okay, however, the result will be better when do we use this one? When do we use this one? The twice standard deviation way. Look at the sample size. But in general, we use the twice standard deviation away from the mean, especially if the sample size is large. Okay, especially if the sample size is large. Now, in this case here, we don't have sample size. We have 5 trials. Okay, we have 5 trials, but when it comes to probability distribution, we always use this one. Okay, we always use this one. This textbook happens to be the same opinion with me. Some other textbook, they actually wonder when to use this themselves. It's like in chapter 3, they use this, but then in chapter 5, they use this one in other textbook. Okay, now, so when is the right way to use the first one? When is the right way to use twice standard deviation away from the mean? In general, twice standard deviation of the mean will be a better use. Okay, only when the sample size is too small, less than 30, then less than 40, but usually if it is less than 30, then we use this one. Okay, the reasoning behind why we use this one is more because it doesn't form, if the sample size is less than 30, then it doesn't get what we call normal distribution yet, which we will learn actually next week. Okay, let's go on. Number 30, part A. Assume, oh, hold on. I think I'm missing some information there. Do they tell us the probability of getting it correct? not, then we assume it's 50%. One second. Yeah. So probability of getting a girl is assumed to be 50%. In reality, it's actually no. Probability of getting a girl is more than 50%. I think it's around 0.56. Well, anyway, with the assumption they give us P equals to 50%. Okay, probability of getting a boy happens to be the same to probability of getting a girl. Okay, and then the n equals to 16. So the number of girls, let x be the number of girls in this among the 16 babies from these 16 couples will be binomially distributed. The number of times 16, probability of getting a girl is 0.5. The question in part A is finding the mean. The mean will be 16 times 0.5. That's, oops, I say 0.5, I write 0.5. That's equals to 8. Okay, and then the variance am I okay right now? I saw just now that my internet connection is not stable. Okay, anyway, so the variance will be 16 times 0.5, that's the P, times the Q, 0.5, that will give me 4. Therefore, the standard deviation is 2. Now then, part D, the one I say, what is the usual interval? The usual interval will be mu minus twice standard deviation, mu plus twice standard deviation. That would be from 8 minus 2 times 2 up to 8 plus 2 times 2. Okay, that's between 4 to 12. Okay. Now, the problem is at this point is, Thomas, how do we interpret this? How do we interpret this? It means if you get 5 or 6 or 7 or 8, 9, 10, 11 girls in these 16 babies, then that's usual. Okay, less than that or more than those is unusual. Now, the issue happens right at the borderline. What happened, Thomas, at 4 and 12? What happened at 4 and 12? Okay, the rule actually they use open interval notation, means not including 4, not including 12. But that's actually some ambiguity here. You can interpret this. Some people, including me, may write it this way, which means 4 and 12 is considered usual also. Okay. Now, the thing is, in reality, we hardly get into this kind of situation. So should we worry about this? No. What happens if we have this question, Thomas, and this result is 4 and 12 part of the usual interval? You can go either way. You can go either way. You can say both included in the usual interval or both not included in the usual interval. Okay, but of course, I do not accept you say 4 is included, but 12 is not. No, it's not. Okay, consistently both included or both not included. Okay, again, the issue is, should we use open interval or should we use closed interval? Do we include the endpoints or not? Okay, do we include the endpoints or not? And the rule of thumb is it's actually up to you consistently. As long as you are being consistent, you include or not. Okay. Now, but of course, most of the time, we don't get such a precise number. We may have, for example, 4.1 up to 11.9. Now, in this case, either you use parentheses, or if you use close parentheses, I mean bracket, either way, you don't include 4. Either way, you don't include 12. Okay? Either way, you don't include 4. Either way, you don't include 12. That's why it does never become an issue in the past. Now, with this problem, it may become an issue. Okay? Now, how to solve this problem? Doesn't matter which way you choose, as long as you are being consistent. If 4 is part of your usual interval, then 12 should be. Okay, this is the situation where, suppose they say 50% chance to get a girl, and of this 16, you end up with 12 girls. And if somebody asks you, do you consider that usual? Is it reasonable? Then I will say, oh, it's iffy. It's right at the borderline. You know, I will not say it's unusual, okay? But I will not say that's common also. It's like right at the borderline. Okay, now that's for this one question. And we basically done with this section. Suggested homework for 5.2. Suggested homework for 5.2 will be, let me look at my textbook again. That will be from number 15 to number 31. So from number, what again? 13. No. From number 13 to number 35. Will be odd ones. Okay, that's for 5.2 binomial distribution. I will go on to 5.3 Poisson distribution. Poisson distribution. Now, in the past, I did not have a chance to teach Poisson distribution in my class up to like around 2 years ago. So if you look at my old tests, you may not see any problems from Poisson distribution. Okay, that's why in your quiz that you need to turn in next week, you have one question with Poisson distribution, at least to train you what you expect to see. But if you also see from my spring 19 test, if you have a chance to look at my spring 19 test, you must see Poisson distribution also there. I remember I start from spring 19, so yeah, around 2 years ago. I start from spring 19 when I taught Poisson distribution. Okay, so let me write this as a note. I did not have Poisson distribution problem in my test to prior to spring 2019. You will have problems from this section. this section. In fact, Poisson distribution is one of another well-known and quite common distribution you encounter in real life. Poisson distribution is a discrete distribution over a continuous domain. Now, Poisson distribution, you will see measures as random variables. Random variable is a random variable for number of incidents. Is a random variable for number of incidents over time or period time is continuous, okay? Period also continuous. Area also continuous, okay? And etc. Now, when we say discrete distribution over continuous domain, the discrete part is the number of incidences. Okay, the continuous domain is over a period of time, over some area. Let's say, for example, the cases where Poisson distribution may apply. For example, the number of customers coming to a store over a period of let's say 2 hours. Okay. Or we can also see the number of typos, the number of typos on a page of newspaper or a page of a book. Or the number of earthquake. Yesterday we have the great, what's that? The great shake, right? So we practice what do we do in case of big earthquake. The number of over the scale of 3 earthquake in a year. Or we can also say the number of potholes. Over in a 3-mile stretch. Okay, so you see The one we are measuring is the probability of the number of customers, the number of typos, the number of earthquakes, the number of potholes, okay? The number of spam call or spam emails you get over a certain period of time. Okay, and actually, it also, I heard, satisfy the number of cosmic rays coming to the Earth over a period of time. Now that's physics. In fact, that's astrophysics. So the application is a lot. What we are going to learn here actually being used a lot by those supposed to be managers in a big grocery store, like Ralph, CVS, okay, for the first one, for the first case here, the number of customers coming to a store, okay, or the number of customers coming to a cashier in a bank, or just like in the grocery store also, because that will then tell us and during what time we need to have more cashiers. You see? Now, notation. Maybe I give you the good news first. Good news. Every random variable with Poisson distribution will explicitly say so. So if we are dealing with, for example, the number of customers coming to the store over a period of 2 hours, they will explicitly tell you follows the Poisson distribution. It's not like binomial distribution in which you have to identify that yourself. Oh, when you toss a coin 6 times, the number of tails will follow binomial distribution, right? Okay, that's you need to come up with on your own. But when it comes to Poisson distribution, they will have to tell you, okay? Even though after some practice, you will realize that the number of arrivals, the number of incidents of a continuous domain will, most of them, not all, most of them will follow Poisson distribution. Okay, notation. Notation. Let X be a random variable with the mean mu be Poisson distributed. And X will be, the notation will be, X will be distributed Poisson mu. Okay, some textbook correctly use lambda. So instead of using mu, some textbook use lambda here. But lambda in Poisson distribution is equal to the mean. And every Poisson distribution, the mean equals to the variance. Only in Poisson distribution. Okay, other distribution, they don't have to be equal. In Poisson distribution, the mean and the variance are equal. Okay. Now, what I will do first is I will do example in notation. Then From there, we learn how to use calculator. After that, we will do problems, in-word problems. For example, let X be Poisson distributed with lambda equals to 2.4. Okay, with lambda or the mean equals to 2.4. Question, part A, find the probability that X equals to 2. That's the probability notation. The calculator notation will be Poisson PDF. We use PDF because this is equal to. If we want only one number of incidents, we use Poisson PDF, just like binomial. If you probability X equals to 2, you will have binom PDF, right? Now your random variable X is Poisson distributed, then you use Poisson PDF. Now the parameters will be 2.4, that's the mean, and then 2, the number of incidents. Okay. Now then, how to use your calculator. Poisson distribution actually right below binomial distribution. So we go to second distribution, you go down, you see you have below binom PDF, you see binom CDF, and then Poisson PDF. After that, Poisson CDF. Okay, here, because that's equal sign, I use Poisson PDF. The lambda is 2.4. The X value is 2. That's the calculator notation, and you get 0.26126, actually 2 seconds. That will be 0.26127. And actually the rest are the same. The rest are the same with binomial distribution. I think the difference is, the only difference between the calculator work, or maybe to be more precise, the possible outcomes of this random variable. If X is Poisson distributed, then the number of possible outcomes actually start from 0, but goes to infinity. It doesn't stop. Not like binomial distribution, the number of successes is at most equal to the number of trials, right? Okay, but here, when it comes to Poisson distribution, the number of successes start from 0, but go up to infinity. Okay, so let's say for example, if I put some story into this example 1, I put the story that the probability, the average number of customers coming to a grocery store in 1 minute is 2.4 customers per minute. Is it possible you have 3 customers going in? Yes. How about 4? Yes. How about 10? Yes. Why not? The probability is small though, because it's far from the average, right? But still possible. Is it possible to have 100? Yes, possible, but the probability will be very small, very, very small. But theoretically, that's possible. Okay, now that's the only difference when Poisson distribution, the random variable for Poisson distribution will go up to infinity, while binomial goes up to the number of trials only. Let's see. Using the same idea I taught you earlier from binomial distribution, I assume you should be able to compute this. Do here part V, probability that x is greater equals to 7. How about part F? Probability that x is greater than 5. Now, when it is equal sign, then you use PDF. When it is up to 5, for example, you use Poisson CDF. Now, how about if you have less than, then you need to do some adjustment. Okay, likewise for this, more at least 7, then you look at the complement, you look at the complement. Okay, let me give you maybe 5 or 6 minutes to do this on your own, right? Okay, using your calculator. So from here, you already have the probability notation. I want you to write the calculator notation and then compute that using your calculator. 1, 2, 3, 4, 5, 6, 7. Let me give you 7 minutes. Let's start with work on the calculator notation and then the result from calculator. This is Poisson PDF 2.45. Okay, let me use calculator now. So Poisson PDF 2.45. I get 0.06020. 0.06020. Part C, probability that the number of incidents is at most 5. That will be Poisson CDF. Right, because it's at most. Therefore, we use cumulative 2.4,5. That's Poisson CDF 2.4 cumulative up to 5. 0.96433. 0.96433. Probability that the number of incidents is less than 4. Let me do adjustment first. Probability that x is at most 3. Right? Less than 4 means at most 3. Right? Can you imagine that? Okay. Use this diagram to help. Use this diagram to help. When we say less than 4 means up to 3. Okay. Then I use my calculator. Oh, I do calculator notation first. That will be Poisson CDF 2.43, not 4, 3. That will give me, oh, I have the same number earlier, so let me just do this. This is Poisson CDF 2.4, comma 3. Enter. That's 77872. 0.77872. Okay, so we move that far to the left so that we will cover in a few. Well, I do it here. So then what next? Probability that at least 7. At least 7, that's, I see here, 5, 6, 7, 8, and on. At least 7 refers to starting from 7 and on. But we don't have a calculator function to help us with that. I need to attack that from the complement point of view. The complement is at most 6. Right? Okay, the complement is at most 6. So what I will do is I write that as 1 minus probability that x is at most 6. That's 1 minus Poisson CDF 2.46. Poisson CDF 2.46. I already have the 2.4. I changed this to 6. 0.98841. So this is 1 minus 0.98841, which will give me 0.01159. Oh, the probability is very small, huh? It's less than 1%. It's like around 1% probability. Okay, so if you have a Poisson distribution, let's say the average customers coming into a store in the next 10 minutes is 2.4 on average, what is the probability that in the next 10 minutes, all of a sudden you have at least 7 customers? Then the probability is very small, like around 1%. So what happened if that really happened, Thomas? If that events really happen, then very likely, well, it is just coincidence, okay? It's just coincidence. But if it happens quite often, then you start questioning if your average actually 2.4. If your store suddenly attract more customers on average, then you should ask yourself what you have done right to have such situation. Okay, to have more customer coming. Of course, hopefully those customers, those arrivals translates into sales, right? What you don't want to happen is a lot of people coming to your store, but none of them buying. They just actually do window shopping. That's so sad, right? But at least they come first. At least they do window shopping first, and we hope it translates into some sales. Last one, probability that x is more than 5. More than 5 refers to starting from 6. Oops, wrong color. Starting from 6. Right? More than 5 means starting from 6. Now, the complement of that is up to 5. So this is equals to 1 minus probability that x is less than equals to 5. It's 1 minus Poisson CDF 2.4, 5. Oh, we happen to have that in part C already. So that's 1 minus 0.96433, which is 0.03567. Yeah, it's still quite rare. It's still quite rare. Not very rare, but quite rare. Okay, because the probability of having more than 5 customers in the next 10 minutes is, if the mean is 2.4, is approximately 3.6%, which is less than 5%. Okay, now that's for the notations, probability notation, calculator notation, and how to use your calculator. Next, let's do a problem from our textbook. There are actually some problems really nice I see here. I mean, I like to go over those. I will start from number of hurricanes first. Let's see this. Give me a sec. Here's the information. This is the information. And then if I do number 6. Number 6. Assume that the Poisson distribution applies. So they have to tell you explicitly, at least for this class, I will tell you explicitly when Poisson distribution, if a random variable follows Poisson distribution, then I will tell you so. Okay. Now, however, it doesn't mean if I don't tell you, then it is binomial. No. It is possible if I don't tell you. For sure, if I don't tell you, then it is not Poisson. But in this class, together with this, we already learned 3 well-known random variable. Actually, let me just write it down. Today we learned binomial distribution. Okay, and prior to this, after this, right now, we learn Poisson distribution. But prior to binomial distribution, last week, actually, we learned one important distribution, not as important as binomial, but important enough. But it has a very, very high level name, such that I didn't tell you the name. Right now, I can tell you the name already. Okay, the name is hypergeometric distribution. Hypergeometric distribution. Okay, hypergeometric distribution has something looks like this. Something like this. This is hypergeometric distribution actually. That's hypergeometric distribution. Okay. That's hypergeometric distribution. But the name is so scary. The name is so scary such that honestly, if I tell you the name too early, it may scares you first. That's why I didn't tell you the name. Okay. Now, in fact, after binomial distribution in our textbook, they mention a little bit about something called geometric distribution, negative binomial distribution. But these two distributions, even though they are actually quite well known, is not as often compared to these 3 distributions in our daily life. That's why you will see I do not emphasize on this. And they are actually quite easy to understand. So if you happen to have some time, you may want to Google geometric distribution. Okay, you may want to Google negative binomial distribution. Okay, but I will not cover that in this class because I rather focus on the things I know for sure important for your life. Okay. Now come back here. They tell us that assume that the mean number of Atlantic hurricanes in the United States is 6.1 per year. Let me define it. Let X be the number of hurricanes in a year. And X will be Poisson distributed with average 6.1 per year. Part A, find the probability that in a year there will be no hurricanes. Part A, find the probability that X equals to 0. That will be Poisson PDF 6.10. Okay, then I use my calculator. You compute that also, please. $0.00224. That's 0.00224. That's the probability of having no hurricane in 1 year. Now, part B, which I don't like to do right now, but I do it anyway. In a 55-year period, how many years are expected to have no hurricane? How many years are expected to have no hurricanes? Let me define a new random variable. We are not talking about the number of hurricanes anymore. We are talking about the number of years with no hurricanes. Let y be the number of years without hurricanes. I want you to realize that this y is now binomially distributed. You have 55 years, that's 55 trials. Either you have hurricane or no hurricanes. 55 years, that's 55 trials. Probability of not having hurricanes is 0.00224. Now then, what is the expected value? 55 times 0.00224. Okay, whatever the probability I have earlier, multiply by 55. I get 0.12336. 0.12336. This is not probability. This is expected value. So with the average of 6.1 hurricanes in 1 year, what is the number of years without hurricane in 55 years? The expected value is less than 1, it's 0.123 something. Okay, so do not then come back to me and say, see, in the last 55 years, we always have hurricane. Well, that's what we expect, right? Because even the average number of hurricanes in 1 year is 6.1. So the probability for us not having any hurricane in 1 year is so small. It's a very rare case. It's less than 1%. Now it's very, very significant. It's very significantly rare. Okay. Now, if you have such a rare event in which in 1 year we have a very peaceful life, that no hurricane in Florida Key, for example, right? That's supposed to surprise you instead. Okay. Yes, hurricane in 1 year is a rare event. Okay. Maybe it's a rare event, but it's not so rare such that uh, it's more rare to have no hurricanes at all compared to having at least one hurricane. Okay. So then if somebody tell me that, oh, global warming, for example, so, and they use the argument of, oh, because we always have hurricane in the last 55 years. Well, even if you look at the data, even when you look at the data, the number of, with that kind of average, even if you reduce this to only 4 hurricanes per year, right, in America, the expectation is still, in 55 years, is still less than 1. Trust me. What I'm saying is this, okay? To argue that global warming happening, regardless you believe it or not, okay? Regardless you believe it or not, to argue from the point of view of hurricane is not correct. Okay? To argue from the number of hurricane, to argue that global warming is happening is correct. Let me tell you first, some story time. Let me tell you first where's my stand about global warming. Okay, but if you disagree with me, you are totally fine. Don't worry about this. Don't worry about this. Okay, I hardly express my opinion about some controversial issue, which for a lot of people are not controversial. It's my stand that is, it's my opinion that is controversial. I do not believe global warming is man-made. That's me. Okay, now of course you can show me all evidence, and I can show you all evidence, a lot of evidence also that goes against what you believe. Okay, and if you Google it, actually you go to Wikipedia, you will have enough number of scientists from Harvard, from MIT, from those well-known universities in uh, in climate study that actually agree with me that global warming, even if it is happening, it's not man-made. Okay. Uh, my opinion is global warming, even if it is happening, it is not caused by human. It is caused by solar flare and volcanic activity underground, especially in the polar region, North Pole especially. Okay, but you may want to look into it. Okay, don't just believe me. I don't want you to just believe me. No. Okay, but if you want to refute me, at least take a look on those also. And then later on, if you disagree with me, that's fine. Okay, but I think what is more important is not about what is my stand about global warming. It's what I do. Remember I said earlier that I don't believe that global warming is man-made. Now you may then say, Thomas, your belief is controversial and against the common belief. Well, unfortunately, science, there's no democracy in science. 2 times 3 is 6. Even before there's enough people don't know that it is 6. Okay? There's nothing called that we need to take vote is 2 times 3 equals to 6. No. Even if the whole world say it's not 6, I still say it's 6. Okay, you want to execute me for that? Do it. I'm a mathematician. I'm not a political science person. I'm not here to make people happy. I just tell you straight at your face, 2 times 3 is 6. Okay? But Thomas, a lot of people say out there that 2 times 3 is not 6. It doesn't matter. It's not democracy. Okay? I don't need other people's approval to talk about that. Okay? But anyway, even though I say global warming, I don't believe that global warming is man-made, okay? And a lot of people, some students actually try to argue that with me. I asked that student, there's one student tried to argue with me in class, of course, about this. I said, I don't mind. I mean, it's okay. It's totally fine for you to have different opinion. By the way, that student ended up with an A also. So you see, that person have a very strong opinion against my opinion about global warming, but still get an A. Okay, so no, that's not an issue for me. That's fine. Now, what I want to say is this. What I want to say is, even though I don't believe global warming is man-made, take a look on first, what car I drive. I drive Prius. If you can drive Tesla, that will be better, even though in my opinion, Tesla's battery, we don't know if that's environmentally friendly or not. I'm not saying Prius is environmentally friendly, but at least because there are a lot of Prius running around, then if something wrong with my battery later on, they should already have a technology to salvage that without what's that? Polluting the earth. Okay. Second, I have websites, a website for my material, so that I don't need to print everything out. I just post it online. Okay? The only thing that I am required to give students in my class, if we have an on-campus class, I'm required to give you a syllabus on paper. Even when I give them quiz or tests in my class, my quiz may be only half page. So when I print it, I print like 1 page, 2 quizzes, and then I cut it into half. Okay, compared to those people who say that they believe global warming is man-made, when they drive, for example, a gas guzzler. And when they print, they make copies. They make copies as if papers are free. Their syllabus is like 10 pages long. What for, man? My syllabus is 2 pages, at most 3 pages. Okay, but I have seen people with syllabus like 10 pages long. I even have seen somebody with 20 pages long. It's like, are you kidding me? Which student gonna read that? I would be happy if they can read 20 pages from the textbook. Right? Okay, and the second one is those people who believe that global warming is happening, they like to buy a house next to at the beach. If you believe global warming is man-made and is happening, then you should believe that if any flooding happened because of global warming, it should happen at the beach first. And why do you buy houses there? I mean, you do things contrary to what you believe. So here's what I say. Here's what I mean. Okay, I don't believe in global warming, but I live as if global warming is man-made. I believe that's better compared to those people who say global warming is man-made, but the way they live as if it has nothing to do with them. You know, okay, so those are the people I get really pissed off with. It's like, what are you talking about? Okay, you talk about this thing, but you do it about something else. That's silly. Anyway, starting from hurricane, we talk about global warming. By the way, remember I said earlier that cosmic ray follows Poisson distribution? Okay, now it is believed that cosmic ray may have some contribution to our global warming. Okay, somebody actually mentioned that, even though I don't think that's significant. Okay, how does result from part B compare to the recent 55 years in which there were no years without any hurricane? So they assume this data is actual data. Okay, in the last 55 years, have we had any year without hurricane? The result is compatible. the expectation is less than 1, then Poisson distribution work. Okay. That's for number 6. Let me see if there's more problems from there, but I guess I will just stop here. Your suggested homework will be from number 5 to number 15. Suggested homework from 5.3 from number 5 to number 15, just do the odd ones. Okay, that's for today. When is your test, by the way?
October 30th.
October 30th, 2 weeks from now. So from today until 2 weeks later, you actually have 2 weekends to 2 weekends to study for your test. Okay, and like I believe I said this before, if your test 2 is more than 50, I'll be happy enough. Even though, of course, I'll be a lot happier if you can get more than 70. Okay, I did have students who get near perfect score or even perfect score in test 2. It happens. It happens. But compared to test 1, test 2 is more difficult. You need to think more, less procedural. And therefore, I want you to start studying for your test 2. Okay? Start doing it this way. This weekend, do the suggested homework and start working on the homework, the homework that you need to turn in next week. We have a homework due next week. I mentioned that earlier, right? Okay. Now, then you will see what you study, the homework that you need to turn in next week actually covers a big portion, if not all, nearly all portion of your test 2. So in between you study for, you actually work on your homework to turn in next week. Along the way, I hope you already study for your test 2 also. Okay? See you then next week.
All right, thank